Welcome to Chapter 13, ANOVAs. So we're still using our decision tree, and we're always going to make a decision about whether we're going to be looking for a relationship or for a difference. So we are still looking at differences, and we have to make a decision. Are the same participants being tested more than once? If the answer is no, then we have to ask how many groups we're dealing with. If we're dealing with two groups that have only been tested once each, then we're going to have that t-test of independent means, which we just did last week. If we have more than two groups, a t-test won't work because a t-test will only use two scores. So we will then be using a simple analysis of variance. Now, much like our t-test, there's a other side to this. And if we come back up here and we go and say, yes, our participants were tested more than once, how many groups are we dealing with? Are we dealing with two groups of scores, or are we dealing with more than two groups of scores? So I like to add this little piece to my decision tree because it clarifies the difference between groups of people and groups of scores. So in this particular case, if I have two groups of scores, I have a t-test for dependent means. If I have more than two groups of scores, I have a repeated measures analysis of variance. So let's take a look at simple analysis of variance. Analysis of variance, simply looking at the difference of means for three or more groups or independent variables. So for example, I can break up student study time for the NCE, look at their NCE score, maybe look at the year that a student's in the doc program and their research confidence, or the weeks they've been in a stats class and their knowledge, okay? So the cool thing about ANOVAs is that they let us look at between group and within group differences. So if I'm looking at say a repeated measures and I have three groups, like say these NCE here for 8 and 12 hours, I could do a pretest, right? Where I give everybody a pretest of NCE information. And then at the end of the either 4 hours, 8 hours, or 12 hours, they take the actual NCE and I look at their scores. I can look at the difference within groups for the people who studied 4 between their pre and post test. For the people who studied 8 hours, I can look at their pre and post, and I can look at the within group for the 12 hours pre and post. I can also look between groups. How did the 4-hour people do compared to the 8-hour people? How did the 4-hour people do compared to the 12-hour people? So I can look at all of these different relationships with one statistical process. Now, ANOVAs aren't going to tell us where the differences are. ANOVA is just going to tell us if there are differences, which is an important distinction to remember. So when I get my F statistic or F score from my ANOVA, it's going to tell me, hey, yeah, there is a difference, or no, not so much. And I have to do additional analyses called post hoc analyses to be able to discern where the difference is. So we're going to learn about all of those in this video. All right, so lots of different types of ANOVAs. You'll see this written in many different ways. A very common one is a simple one-way ANOVA, but we also use factorial ANOVAs, which we'll be talking about in the next video. And then MANOVAs, which we'll be talking about in future classes. So let's go through an ANOVA, okay? So one of the things that's important to know is that we're going to have our treatment. We'll have more than 2 levels of a grouping factor, so more than 2 groups, and then we have to look at differences across their average scores or means. The F statistic formula is the sum of means between and the sum of means within, which is the same as saying the variance between groups and the variance within groups. Now, we're going to look at this particular example where we're looking at preschoolers and their language scores. So this group, group 1, spends 5 hours per week in preschool, whereas group 2 spends 10 hours and group 3 spends 20 hours. So we're going to state our null hypothesis, which of course there is no difference, right? So I would say in words, there is no difference in preschoolers let me try that again. There is no difference in language scores of preschoolers who spend 5, 10, or 20 hours a week in preschool. I'm going to have a 0.05 significance level. And then when I do my ANOVA, the decision chart, I come up with an ANOVA. And so I'm going to calculate that. So here we go. So whenever you're doing ANOVAs, definitely use your charts. Charts are your friends, and they will help you come to all of the types of data that you need to have. And it keeps you very organized. I've seen people try to do this freehand, and usually they end up with the wrong answer. So I strongly, strongly urge you to try to do this with the charts. Okay, so here's my first set of data. I'm going to square each one of these numbers, and that's going to give me this column of data here. So 87 squared is 7,569, 86 squared, 7,396, etc. Now, for my ANOVA formula, I'm going to need the summation of x. So I am going to sum up this row, which is 766. I'm also going to need the summation of x squared, which is this. So I'm going to sum this one. Then I'm going to repeat that for groups 2 and 3. Okay. Now I'm going to bring down the summation of x for group 1, for group 2, and group 3. And that here is going to give me the summation of x, because if I sum up the summations of x, I'll get the summation of x. And here's my means. I'm going to do my means. And then I'm going to do the summation of x squared, which is this right here. So I'm going to bring down group 1, group 2, and group 3. And that summation of x squared is this green one. And I'll tell you why I have colors in a second. Okay. I also need the summation of x squared here. So the summation of x squared. So I'm going to square this, and then I'm going to divide it by capital N, which is the total number of people in my study. So that would be 30. So I'm going to take 2,534, and I'm going to divide it by 30. And that's going to give me this number. All right, so we squared this number, and then we divided it by 30, and that gave us this number. Now we're going to do the summation of x squared divided by n. So this is going to be this summation right here divided by this n, okay? And I'm going to do that for group 2 and group 3. Boom. And then I'm going to add those up because I want the summation of those, and that is going to give me this number. It seems complex, but if you follow the steps and you use the charts, it can actually be simple. Oh, I need to highlight this again in blue. I'll tell you why in a second. There we go. Okay, because this can get kind of confusing when you're developing the between sums, the within sums, and the total sums. I've color-coded this so you can see where they're different, because it's really easy to kind of mistaken which one you're doing. So you can see this one's here and this one's here, and that goes with this one. The yellow ones here and here match this one, and the green ones match this one. So I hope that helps you kind of bring the right numbers down in the right places. So we're going to bring those numbers down. No, I don't want to unhighlight everything because I don't want to get rid of those numbers or those highlights. There we go. No, just this part. Okay. And then we're going to do this number minus this number, this number minus this number, this number minus this number. And that's going to give us our between sum of scores, within sum of scores, and our total sum of scores. So I'm going to unhide those. Boom. Now I'm going to bring these down into my formula in just a minute. So I've got this other chart that will help us. So I'm going to bring this information right here, these three numbers here. So I'm going to put those here. Now, K is the number of groups that I have, or observations. So in this particular situation, I have 3 groups. So I have 3K. So my K is 3. All right. And then my N is my total number, right? My capital N is my total number. So that's 30 minus 3, which is my K. And then my total sums is this one plus this one. So my total sums, of course, is the sum of squares for both of those. So that's those added together. Now, how do I get the mean sum of squares? Well, the mean sum of squares is going to be this number divided by my degree of freedom. This number divided by my degree of freedom. So I'm going to give you both of those. All right, now I can do my formula. So I'm going to calculate my formula, which is my mean sum of scores between and my mean sum of scores within. So 566.49 divided by 64.39. And that gives me an obtained value of 8.80. It's actually 8.799, but we'll round up and that'll give us 8.80 because we can round to 2 when we're in our final step. Now, we've already calculated our degrees of freedom. So we need to go to the back of the book, which I forgot to open as always. And so I'm going to open that really quickly. And we're going to go to the third table in our library. And we're going to look up our Anova value, our F statistic. Okay. Because I'm doing this by hand, I have to look up a critical value. I know that if I were doing it in SPSS, SPS would tell me the exact significance level. But because I am doing this by hand, I'm guessing, right? So I'm going to try to use 0.05 as my critical value and or my alpha level. And I'm going to use that to determine my critical value or my cutoff for my fail to reject zone. So B3 critical values here, if you forget how to do the degrees of freedom, it explains it here. But our numerator for ours is 3 minus 1, which is 2. So we're going to be looking at this column right here. And then we're going to be looking for our denominator, which for us is 30 minus 2, which is going to be 27. So we're going to scroll down till we find 27. Here's 27. We're going to go to the second column in the 0.05 row. And our critical value is 3.36. Now I know that my observed value was 8.80. So I could report that it was significant at the 0.05 level, right? By using this. But if I look here, I see that the critical value for 0.01 is 5.49. So it would be more accurate to report that it is significant at the P less than 0.01. Because I'd be using this critical value. Hope that makes sense. But remember, we only do critical value when we are doing it by hand. All right, so I've got my 3.36 because it's still at 0.05. And then I'm going to make a decision. There's less than 5% chance that one of the tests, the average score of each group, differ due to chance alone, but rather because of the treatment or the time in preschool. So therefore, the 3 groups of preschoolers demonstrated differences in language scores. And I would report that with my data, and I would put F, and then I would put 2,27 equals 8.80. And it would actually be accurate, like I said, to report it at 0.01. And there we go. I would subscript this, just this part. So I'm going to subscript that part because that's my degrees of freedom. And really, if I was using this result, this would say there's a less than 1% chance, right? And this would be a 1. Okay, that's if I do this 1. If I had done it using this, it would be 0.05. Okay, so here I've now based it off of more accurate to use critical value. What was that? 5.45. No, was that right? 5.49. 5.49. 5.49. P less than 0.01. Okay, so all right, so there we go. So that is our Anova. Now, sometimes people will ask me why we don't run multiple t-tests. If I have the same data, right? So I've got these 3 groups. Let me insert a table here to show you what I mean. Okay, so I have group 1 preschoolers, right? Group 2 preschoolers, and then group 3 preschoolers. And so sometimes students are like, well, why don't I just run a t-test to compare group 1 to group 2, group 1 to group 3, and group 2 to group 3? Well, that seems simple enough, but every time I run the data, I'm increasing the chance that chance is coming into play. So what I want to do instead is run an ANOVA. But if I were to run this comparison of group 1 to 2, group 1 to 3, and group 2 to 3, I have to then adjust my alpha. So I use this formula to adjust my alpha. So if I start off with a 0.05 alpha, I'm going to have to raise it to the third here, 1 minus that alpha, and raise that to the third because of the 3 observations that I have here. So that's going to actually give me a 14.26% chance. The chance is at play and not what I actually studied, in this case, time in the preschool. And this is far unacceptable for social science research. So we need to stay under 0.05. So that would be important to know. This is why you can't run multiple t-tests on the same data. Now, effect size. Our effect size is in an ANOVA is called an eta square. So this is an eta, this is the Greek letter eta. So eta square is our effect size for a one-way ANOVA. And here's how I interpret that. You can see it's interpreted a little different than Cohen's D, which we used for the T scores and the Z scores. So this is our effect size for a one-way ANOVA. So how am I going to calculate that? I'm going to take the between group sum of scores from that table up above and the total sum of scores. So I'm going to punch those in and solve, and it's going to give me an eta square of 0.39. And when I look at the interpretation, that is a large eta. And the way that I would write that is for eta squared, 0.39 is a large effect. Okay. Now let's do some practice. Let's go into SPSS and see how to run this in SPSS. Okay. So I am going to bring up my SPSS. There we go. So this is the data from SPSS, okay? And I'm going to leave the directions here so you'll be able to see it. Now, if you had to enter the data, you would, but I already have the data entered. Now, what do you notice about how I entered the data? This is really important. This is like our independent t-test. When we're running those tests, we have to group our data. Okay, so I have group 1 here and their data, group 2 and their data, group 3 and their data. And on my variable view, I have my group. And then here I've coded my group using the values. 1 is 5 hours, 2 is 10 hours, 3 is 20 hours. This is a nominal number because it's a grouping number. And this is a scaled number because it's their language score, which I do know that's an equal distance between each point on that scale. All right, so I've got that in here. Now I'm going to go to Analyze. I'm going to go to Compare Means. And then I'm going to go to One-Way ANOVA, which is here at the bottom. Click that. And that's going to bring this. Now, our dependent list is what we are studying, and our factor list is going to be what we're grouping it across, right? That's how we're dividing. So think of factors. How are you dividing this? So I'm going to put my grouping here, and I'm going to put my language score here, because that's what I'm trying to see how that's affected by the amount of time that a preschooler spends in the in preschool each week, right? So hit OK. And that's going to bring up my data, which might be hiding somewhere. There it goes. It's coming up over here. So this is my source table for my ANOVA. So this is called a source table. This is where I'm going to get my information. Okay. And what I'm interested in is this F score, which is the exact same thing that we found when we did it by hand. And it's significant at the 0.001 level, right? 0.001 level. Now, if I wanted to, I could also run this again. Let's do it again. I've got these things in here. I wanted to estimate the effects size, so I'm going to click that. I'm also going to click post hoc. Now, the most common post hocs we use are LSD, Bone-Ferroni, and Tukey. I like Bone-Ferroni. There's really not much difference. You can run multiple ones and you'll see they're about the same. And I'm going to hit continue. Okay. I don't think there's anything. We could get our descriptives if we wanted to get some of our tests for our assumptions to make sure that we could in fact run this, we would. And we want a confidence level of 95%. So let's just click the descriptives just so you can see it. We'll hit continue. And now I've got my post hoc selected, I have my descriptive selected and my source table. So let's see how it looks different. It's going to come up on my other screen. I'll bring it over as it's calculating. Hopefully your SPSS is not as slow as mine. I'm doing it through a VPN, so it like has to call in and solve it and then calls back with the answer. All right, so here's my descriptives, which are really helpful when you're reporting your data. How many, mean, standard deviation, my confidence interval, and then minimum and maximum. I really like to use minimum maximum because if I have a range of scores that I know my scores are supposed to be in, it gives me a quick check to make sure there's no errors, right? At least at either end of the data. And then here's my source table. Again, same information with my F score, my significance level. Here's my degrees of freedom. Okay, now here's the effect size. So it's giving me lots of different ways to do effect size, but we're just worried about eta square. That's really the one that we're going to focus on, 3.95. And again, here's if I were to estimate where I thought the real true range was of my effect size, this is where it would be. But this shows a very large effect for an ANOVA. And then here's my post hoc. And this is where I get to find out where the differences are. This tells me there is a difference, but it doesn't tell me where the difference is. The post hoc tells me where the difference is. So what it does is it creates what we call pairwise comparisons. So this is 5 hours, the group for 5 hours compared to the group that spends 10 hours. And there's a mean difference of negative 8.6, right? So that tells me that the 5 hours are doing a little less than the 10 in language performance. The 5 hours are doing a lot less than the 15, but what I have to check is my significance level. What is my significance level? Well, I find that there's not a significant difference between the 5 to 10 hours. So there really isn't that much difference, but there is a significant difference for the 5 to 20 hours. Now let's find the 10 to 20. So here's 10 to 20, and I see that is not significant, okay? This one is the same as some of these. So this is just 20 to 5. So this is the opposite of this. So it's like a mirror image. So I can see 20 hours to 5, they average 15 points higher on the language scores. And that is a significant finding. Okay, so I would report my post hoc saying that there is a significant difference between preschoolers who spend 20 hours and those who spend 5 hours. I would put mean difference of, I would put M and then a capital D subscripted equals 15 into comma, p-value 0.001 into parentheses. Okay, so that would be the way I would document my data. Okay, remember if you see this asterisk, that means it's significant at the 0.05 level. And in some times when you see articles, you'll see a double asterisk for 0.01 and the triple for 0.001, but for SPSS, it just means it's significant at the 0.05 level. Let's go back to our document. So this is the same results that we had when we did our finding. And then this is how I write my results with my results in there. It was two-tailed because I didn't say which way, right? And this is a formula for you on how to write your results.